Have you ever been a victim of bicycle theft in Waterloo?
Yes!
Do you sometimes come back to a broken lock? Well, not anymore. Introducing new, portable, affordable, durable, and sturdy U-Lock, made just for you. Consumption of U-Lock may lead to high levels of wanted such as the ECE, Tron, or systems. Please consult a doctor if you're experiencing symptoms. A team of the world's best engineers got together and began performing a needs analysis. They began with a problem statement for a portable, affordable, durable, and sturdy U-Lock that wouldn't allow thieves to insert cutting tools. Before proceeding, they analyzed the environment and situation, and thus stated their assumptions in design, such as how thieves would pull the bottom of the lock with their hands, and the lock fails if it deflects enough to fit cutting tools. It is also assumed that the bike frame and the bike stands are made of steel. So that means it's going to be outside, exposed to rain or snow, and also in contact with dissimilar metals. Sounds like galvanic corrosion to me. In order for this to work, we need low to no deflection, good stiffness, high yield strength, and good fracture toughness. We don't want it to deform, and we need it to withstand that pulling force even if it gets cracked. We also want something that's durable, that resists that galvanic corrosion, something that's lightweight and affordable. It also needs to be able to bend into the U-shape.
Some of the other properties that are important for our U-Lock include the U-Lock's fracture toughness and also the hardness measured in Vickers hardness.
We want all of this for our U-Lock with a mass under 1 kilogram and a low cost. Before designing, we did some research. We read online articles comparing U-Locks as well as measured different locks we found. Since we want to design a U-Lock that will limit deflection and prevent thieves from putting cutting tools inside, we want a small U-Lock with a high cross-sectional area. This way, it's most snug on the bike. We came up with some functional and geometrical constraints to help us derive our MPI by isolating our mass variable. Yeah, we did a lot of math to get our MPI. What is MPI, you ask? It's our Material Performance Index. We use CES software and Ashbury diagrams in order to plot lines with our MPI and figure out what materials to use.
When determining the MPI of our U-Lock, we actually simplified the shape of the design into 3 components: the curve and the 2 straight legs on the U-shape. For the curve, we are assuming that it is acting in the same manner as if it was a straight beam, while the 2 legs acting as tie rods. Some of our constraints are that it must support a load of F, it must deflect less than a value delta, we know that its length is specified, and also that its width is specified. Our objective, in this case, is to minimize the mass of the beam. However, our only free variable in this situation is the thickness value, h. Full detailed explanation of how the MPI was derived, please see our supporting document. The rod experiences the same functional and geometric requirements of the beam. However, the specific values that were used in the MPI calculation were changed. Kind of aluminum would be best suitable for our application. After our team of engineers comprised a list of aluminums that would be able to withstand the forces and the conditions that a U-Lock would be subjected to, the list of materials were further down eliminated based off of price, durability, more specifically the material's resistance to corrosion, its fracture toughness, machinability, and hardness. The hardness of the material, and also the cost of the material, were the next 2 most important attributes. Ultimately, aluminum 6060 that has been T6 tempered was chosen because of its high hardness value and also its low price. For a full detailed explanation of why T6 tempered 6060 aluminum was chosen for our application, please see our supporting document.
Upon cold working, aluminum 6060 alloy deformed into its design shape, in this case U-shape. Cold working processes increase material's dislocation density, and therefore strain hardening comes into play. As aluminum 6060 is reshaped and gains strength, its ductility is compromised. Thus, annealing is required to restore its ductility and relieve cold working residual stress. There are 3 steps in edge hardening to maximize the material performance through controlling precipitations, distributions, size, and shape. So there are solution treating, quenching, and aging. Solution treating. After cold working, aluminum 6060 is then heated up to a temperature below its melting point, at which the material's microstructure is in the form of solid solution, one phase. The alloy microstructure undergoes recovery, recrystallization, and grain growth. Thus, the deformation energy is relieved and materials become more ductile. Quenching. After solution treating, the alloy will start fresh with non-microstructure. The alloy is then quenched to a temperature that no longer allows materials to stay as a solid solution. The second phase exists in laminar structure, which is useful for diffusion process. Aging. To control the precipitation process, the alloy will be heated up again, but to a temperature that is lower than those for solid solution phase. At the end, aluminum alloy will be strengthened through controlled precipitation hardening. Coating. Based on the fact that the U-lock will likely to be in a natural environment with contact to air and water, it will corrode. Therefore, it was decided to anodize the aluminum alloy to protect it from corrosion. Other bonuses include good appearance and resistance to wear. Here are some useful aluminum 6060 material properties which will be used to determine heat treatment temperature based on phase diagrams. Its main compositions are aluminum, magnesium, and silicon, and its melting temperature is between 610 to 655. Its recrystallization temperature would be 30 to 40% of the melting temperature. In this case, it is from 183 to 262 degrees Celsius. So the proposed schedule is: first, we saw cut an aluminum alloy sheet with a thickness of 0.583 centimeters to a width of 1.905 centimeters. 0.583 centimeter is the standard. Secondly, we're gonna roll banding the material to a U shape with a vertical side length of 12.7 centimeters and a bottom curve length of 15.24 centimeters at 220 degrees Celsius. So the process is similar to what is shown in the diagram. The temperature of 220 degrees Celsius is chosen as it is lower than the recrystallization temperature. Thirdly, solution treating. Anneal the material at 450 degrees Celsius for 1 hour. The temperature at 450 degrees Celsius is chosen as the alloy will form a solid solution in the phase of aluminum at this temperature, which is also shown in the phase diagram. For the fourth step, quench the material to a temperature of 180 degrees Celsius for 30 minutes. Laminar structure of magnesium silicon starts to form. Such structure helps with diffusion. The material is strengthened with precipitation strengthening as there are two phases in a microstructure. Aging, the fifth step. To control the precipitation of secondary phase, heat the material up to 250 degrees Celsius for 1.5 hours and avoid overaging. Therefore, an aluminum alloy with controlled strength is formed. 250 degrees Celsius is chosen as it is below temperatures for solid solutions. 6. Anodize the alloy at room temperature 25 degrees Celsius. Use sulfuric acid, approximately 15% by weight, 10% by volume, at 10 to 20 volts to create an anodizing thickness of 0.0001 inches.
As engineers, we had a lot of different combinations and designs. We tested our initial designs, and they failed. U-locks were broken, bikes were stolen. But we finally got it. We designed a snug and tight U-lock that doesn't allow for deflection under the assumed environment. Nobody can break through it. And finally, we chose AL6060 because of the material performance index, because it ran through our filters on the CES software, such as hardness, corrosion resistance, fracture toughness, and cost. And once we chose this, we cold worked it to bend into the U shape, and we age hardened it to strengthen it. Lastly, we coated it using anodization to prevent corrosion, wear, and have a better appearance. Please note that if the environment changes, if the bike post material changes, or the bike structure material changes, this U-lock would perform differently. Also note that we are not legally responsible if the whole bike is stolen except for the U-locked part.